Mba633 instructional video prepared by Professor Amit Dada, School of Management, George Mason University. In this segment, we'll continue our discussion of confidence intervals and see how one goes about determining the confidence interval for the population mean, but this time without knowing the population standard deviation. In other words, sigma is unknown. And we look at the same problem as we did in the previous clip. In other words, I want to find the average time taken to fill out the federal tax return. So that's the same population as before. We are assuming that it's an infinite population. So I still want to find the average time taken to fill out the federal tax return. But unlike the previous problem where we said we knew that the population standard deviation is 9 hours, this time we are saying, well, I don't really know what the population standard deviation is. So then how do I go about determining an estimate for the average time taken to fill out the federal tax return? In other words, getting a confidence interval for mu. So I still go back to my 40 people and I look at the 40 numbers they gave me. Each person told me how long they took to fill out their federal tax return. And if you remember, in the last problem we said that the sample mean was 33.5 hours. So the average of the time taken by these 40 individuals was 33.5 hours. But then when we worked the previous problem, we went on the assumption that the population standard deviation is 9 hours given to us. Now, if you don't know the population standard deviation, what's the next best thing that you can do? The next best thing you can do is use the sample standard deviation as a proxy for the population standard deviation. In other words, I look at the standard deviation of these 40 values. That's represented by the letter S. S is the sample standard deviation, and that's 13.65 hours. That's from the computation in the sample. Since I don't know sigma, the population standard deviation, I'll say, hey, that's my best guess of the population standard deviation. Now notice that since I have substituted a sample statistic S in place of this certain population standard deviation that I knew for sure in the previous example, I have introduced more uncertainty. Basically what that does, if you think intuitively, if you introduce more uncertainty, the probability distribution becomes fatter, becomes wider. So now the distribution of the sample mean, which in the previous example was normal, okay, becomes a little shorter and more fat. Okay, so it's a little fatter than the normal distribution. Why? Because I had to substitute a sample statistic S instead of the population standard deviation, which I don't know anymore. So when the population standard deviation is unknown, then the sample mean is no longer distributed normally. It follows what is called a t distribution. Now, a t distribution, you can look at the other video clip that we have on the t distribution and the Excel built-in function to compute those probabilities. I will not repeat that here, but the sample mean is distributed according to the t distribution, which is also a bell-shaped curve, but it's a fatter bell-shaped curve compared to the normal distribution. Why? Because we are substituting S in place of sigma. Okay. Now every t distribution has associated with it something called degrees of freedom, and degrees of freedom, df, is simply the sample size minus 1, n minus 1. And you know, if the sample becomes large, typically if n is more than 100, then we say for all practical purposes the t distribution is the same as the normal distribution. Obviously, the larger the sample, the less the uncertainty introduced by substituting S in place of sigma. Okay, so if the sample is small, then I introduce more uncertainty by substituting S in place of sigma. Okay, other than that, the logic is exactly the same as before. So let's say I want to build a 97% confidence interval for mu. So I want to be 97% sure that mu lies between the upper and lower limit that I compute. So that's the confidence interval I want to compute. So you remember the trick was to compute the margin of error. Okay, so how large should the margin of error be? So you remember from our previous discussion, the upper limit and the lower limit should be set in such a way that the area, this yellow shaded portion, should be 97%, because I want to be 97% sure that the parameter that I'm trying to estimate, namely mu, lies between L and U. Obviously, since I've introduced more uncertainty and this bell-shaped curve is squatter and fatter, these L and U will be a little bit wider spread out. Okay, let's see if that indeed turns out to be the case. Now, if this yellow portion is 97%, the two tails together is 3%. Okay, so how do I compute U and L? You remember the trick was to first compute the margin of error. How large should the margin of error be given how sure I want to be? I want to be 97% sure. So let's see how large the margin of error needs to be in standard deviations. All right, so for that we will need to use the T inverse. I know the probability and I want to find out my position on the x-axis. So instead of norm S inverse, I'm using T inverse because the distribution is a T distribution for the sample mean, not a normal distribution anymore. So look at the inputs that you have to give. You have to give a probability. What is it the probability of? Now go back and look at the video clip on T distribution and the Excel built-in function and you will see the details there. But essentially the probability that you have to give is the probability of the two tails together. If I want to be 97% sure, the middle yellow shaded portion is 97%. So the two tails together is 3%. Okay, so I provide 3%, and degrees of freedom here is sample size minus 1 is 39. Okay, so I get 2.25. If you remember, for the normal distribution, if I remember correctly, it was 2.17. Now it is 2.25. It has become larger as one would expect because I've introduced more uncertainty. The physical interpretation of 2.25 is that if I want to be 97% sure, then my margin of error has to be 2.25 standard deviations large. Now I know that one standard deviation in this case is 2.16 hours. How did I get this? You remember the standard deviation of the sample mean, sigma of x bar, right? That's the notation that we had. Standard deviation of the sample mean. If you remember previously, it was sigma divided by square root of n. The population standard deviation divided by the square root of the sample size. Here, since I do not know this, the population standard deviation, I have substituted the sample standard deviation in this place. I have substituted S in place of sigma. So that's where my 13.65 came from. Since I don't know the 9 anymore, 13.65 divided by square root of 40, which is 2.16 hours. So for this particular problem, the margin of error in hours would be 2.25 multiplied by 2.16. Since I want to be 97% sure, my margin of error has to be 2.25 standard deviations. One standard deviation is 2.16. So if I multiply the two together, my margin of error has to be 4.86. If I remember correctly, in the previous problem, the margin of error was 3.2 or 3.6 hours. In this case, it's 4.86 hours. It's larger, as I would expect, since I've introduced more uncertainty. Okay, so now that I have this calculation, I am 97% sure that mu lies between 33.5 plus or minus 4.86 hours. Okay, so let's see if that writing comes back. It didn't here. Let me get the pen over here. 4.86 hours. I'm sorry, my machine is an old machine, so it's doing too much computing trying to record what I'm saying and the handwriting that I'm doing, so it slows down from time to time. So the confidence interval here is 33.5 hours plus or minus 4.86 hours. So that would be, let's say, roughly 4.9 hours. So 29.6. Okay. And 34.4. Okay, so if I just approximate 4.86 hours to Oh, I made a mistake. Sorry, I can't add properly here. Um, and this is also incorrect. Maybe I shouldn't try to do this calculation while my machine is slowing down so much. Anyway, you can do the calculation yourself. So the confidence interval is 33.5 plus or minus 4.86 hours. The main thing I want you to see is the logic of computing the confidence interval is exactly the same whether or not you know sigma. So the only difference is you substitute the t distribution instead of the normal distribution when in computing the margin of error. So the basic process is the same. Tell me how sure you want to be. Based on how sure you want to be, I will tell you how large the margin of error has to be in standard deviations. Then I will compute how large one standard deviation is based on the sample size. Okay, and then combine those to get the confidence interval. Okay, so this is how you go about computing the confidence interval for the population mean when the population standard deviation is unknown, which is most of the time.